Okay, reviewing a little bit of what we've gone through so far. We've left the capacitors, capacitance. We noticed that what happens when you have a capacitor in an AC circuit, you get a reactance when you impose a voltage, an AC voltage, which is a time-dependent, time-varying voltage. And what happens is that you get the current leads the voltage across a capacitor because the capacitor needs time to charge up. And therefore, it starts with a current that runs through it, and that builds up the voltage. So that voltage is delayed relative to the voltage that's imposed by the source. Okay. And because it's delayed and because it's there, you have a reactance, which we call, actually we designate as large X sub c or chi. If you know Greek, chi sub c. And that reactance value actually is equivalent to a resistance value for a resistor. In other words, it cuts down on the amount of current that can run through that capacitor circuit, and it also changes the voltage timing and the current timing. Okay. So that's what we talked about with the capacitive. And today we look at what happens with an inductor, which is basically a coil wrapped around either an open tube or a actual magnetic core, usually of an iron material, a steel material, creating a magnetic moments through the coil and the bar, and that causes a magnetic induction. And just like we had for a capacitor, we've got the same type of thing happening with an inductor, only now we call it an L over R constant, which is a time constant. All right, but what happens here, instead of charging up something to create an electric field, we're actually charging up something to create a magnetic field, okay, because we're creating a magnet. And that takes time as well, all right? But the building up of the magnetic field is different than building up of an electric field, because building up a magnetic field requires a voltage change. In other words, the change in voltage will create a current level. In order to get that current up, we have to keep changing the voltage. So by changing the voltage in time, we actually build up a current through our inductor until we get to a quantity where it opposes the set current to a greater extent, and the voltage is stabilized. Actually, the voltage is stabilized. It's equivalent to the line voltage. So again, we have an L over R constant, which gives it's a unit of time, and just like it is in the capacitor case, five times the time constant will give you the amount of time required to charge up an inductor. just like it takes 5 RC time constants to charge up a capacitor. And what we say here is that once it's charged up, we've actually stored energy in the in the case of an inductor, we've stored energy as a magnetic field, and then the change in the case of a capacitor, we've saved some energy in an electric field, and those are reclaimed afterwards through a time cycle that's of alternating current. Okay, so the beauty of inductors, though, the inductors are important when we talk about motors and generators and especially transformers. Okay, so we'll learn about transformers as well. All right, so we'll get to that.